Hi all, this is Purnima Magalingam and you're watching video lecture series on solar and wind energy system. Today, in this video, we are going to discuss about solar resources, particularly voltage and frequency operating limits. Come, let's go into the video. Here, first, let's recall the previous session. So first one is, we are going to see what is voltage frequency operating limits and networks integrated issues. This is the first we are going to recall about last classes. So this particularly deals about which explores the critical voltages and frequency limit, which is essential for grid stability. Well explains the challenges from distributed energy sources. These are the main thing today we are going to discuss. Let's go into the video. First thing we are going to discuss is voltage. Grid stability fundamentals. First part is voltage. So what voltage plays main role in grid stability fundamentals. So it is an electrical potential difference power flows. So it is critical for equipment operations. The main thing is it's critical for equipment operation. The next one is frequency. What frequency plays role in grid stability fundamentals means it rate of AC current cycles. We know the rate of AC current cycle, example 60 hertz. So when it comes to the India, we have only 50 hertz frequency, and it ensures the equipment synchronization. So ensures the equipment synchronization, which is important. So frequency matching with the grid is very important for this sources. Next part is what is an important thing we need in grid stability. That is a crucial for efficient power transfer, the power transfer which prevents equipment damaging and blackouts. So very important is efficient power transfer is very important, and preventing equipment damages and blackouts. We have so many case study about the blackouts, etc. And this is one of the important stimuli. These are the fundamentals. Now coming to the voltage operating, what are the challenges? So we have listed the four challenges. One is voltage limits, and what are the voltage limits? And voltage rise, voltage sag, voltage swell, and harmonics, etc. Here comes uh, first, what is voltage limits? So here it is known as ANSI and C841, which is specific for voltage limits for limitations. So specific for voltage limitations of plus or minus 5% ranges. Voltage ranges from plus or minus 5% ranges. And voltage rise. So voltage rise, what happens? Main challenge is higher DR penetrating to exits limited. So the exceeds the limits, what happens with it falls immediate damages to the systems. Okay, the next one is sag swell. Coming to the sag and swell, which is the functional from intermediate del. So what happens is intermediate, so suddenly voltage get rises and suddenly voltage drop down. These are the challenges we are facing. So what is this? Are this one some of the empathy part we are seeing in this. And the next last main important is what empathy is harmonics. Harmonics plays a major role in this power flow power quality process. So inverters introducing waveform distance. So when we are introducing more number of inverters, what happens? This plays a major role in producing the harmonics, and it automatically finally it goes to the harmonic distortions. So these are the main four challenges we are facing. This main empathy part we are discussed in this topic. Now coming to what is the frequency of challenges? Here comes the challenges of frequency. First is frequency limit. Frequency limits. Here we have an NE as a national energy requirement standard of about 59.95 hertz to 60 hertz. So this comes in a worldwide around, but our frequency limits is 50. So plus or minus 250. And the next one is reduce inertia. So IBR displacement lowers systems inertias. And the next one is frequency executions, how the frequencies are executions, which is larger and faster, and which is deviations occurs. And the last one is oscillators. Oscillators, one of the main challenges for frequency disturbance. Subsynchronous with large wind solar forms. So these are the main four challenges. And now coming to what are the impact of new technologies. So we have now we have a defined part. We have we are in defined part. What is an impact of new technologies? Here it is. Distributed, we have seen distributed energy resources. So we have seen the distributed energy resources. What comes under this distributed energy resources? So we have a solar PV and wind farms having variable output. We know that solar PV and wind farm have a variable output. That is what is distributed energy resources. The next one is uh, inverter based resources lacks rotational inertia. So inverter based, we already seen that inverter based resources lacks rotation inertia. This also plays an important role. And impact of new technology. And second one is electric vehicles. So what about this electric vehicles happens? The high charging demands and creates localized spikes. So this localized spikes also affects the frequency part, and causes grid cognitions and voltage drop. So automatically it affects the grid part. What happens? The voltage will drop or voltage will rise. So there will be some of voltage sag. So there will be issue in power quality. And the next third technology is energy storage system. This is the need of the hour of energy storage systems. So what happens here is batteries offer fast frequency regulations. So in it, what it affects in energy storage system is it battery offers fast frequency regulation that it will affects the entire systems. And the next one is provide crucial voltage supports. It provide the crucial voltage supports. These are the main two things of impact of new technologies. Now here comes the main part is an ideate part. So mitigate, what are the mitigating solutions we are saying? We have an ideate part. First thing is we have four stages of idea. One is we are using advanced inverters, and the next one is fact devices. By using these advanced inverters, rather than using the old method of inverters, because old method of inverters produce the harmonic distractions. This will affect the quality of the power. So by using advanced inverters and by using fact devices for demanding site managements and grid monetization. These are the four main part of mitigation, ideate part. Now here comes what about advanced inverters? We have provide synthesis inertia and voltage regulations, and for fact devices offer dynamic voltage supports. So you know that from solar and wind we have a dynamic output. So fact devices helps us to rectify the problem of offering dynamic voltage supports and shapes the load profile with smart uh, devices. And the last one is grid monetization. Grid monetization is a real time control via sensors and smart meters. So these are the four ideate parts of the mitigation stage solutions for the problem. Now, coming to regulatory and market frame. So what happens here? Regulatory and market frame. We have first thing is IEEE standard. So we have IEEE standard I 1547. We have some standard with mandatory advanced inverter functions. We are choosing the advanced inverter. It should satisfy these standards. Okay. And FERC standard or orders of double four enables DERs in wholesale markets. So next one is state interconnections. So rural wires impacting the distributed energy resources integrated. So these are the regulatory and market framework. The last one is ancillary services, which in civil and centralized frequency regulations. So frequency regulations plays an important role in this process. Okay. Now coming to the conclusion of and the future work. So first we are going to see the collaborations. From the main things, so continuous efforts among stakeholders is vital, plays and vital roles. And next thing is future research work. So what are the future research works in this? Is focus on AIML and inverter optimization. AIML is artificial machine learning is plays an going to plays a main role in future renewable energy sources. And uh, what trends we are following here. That is decentralization and integrations and residential grid. So residential grid in almost in all our foreign countries, the residential grid is plays a main role, and that comes in trends. And the next one is what key take away from this PPT is VBIF limits ensures grid stability. So voltage and frequency, which ensures the grid stability, and the new techniques brings challenges and opportunity. By using the new techniques, we are facing so many challenges, and we are facing so many opportunities. Uh, with this, we are going to wind up with this topic. Here we can let's summarize the topic. First thing is uh, voltage frequency limitation. So what is voltage frequency limitations? We have a grid stability fundamentals and operating voltage operating limits and challenges, frequency operating limit and challenges. What are the so impact of new technologies and mitigation strategies? We have seen four mitigation strategies. That is the main thing is an ideate part and regulatory and market framework, and finally conclusion. Here, what are the grid stability? We have seen grid stability. We have voltage, frequency, and important. So in voltage, electric potential, powers, criticals, and frequency, we have the rate of ACs, ensures implements, and importance is crucial for effect power transfer. We have this is important and prevent equipment damage and blackouts. Okay. And coming to a new implement of new technologies, we have three technologies. One is distributed energy sources, one is EV, and the next one energy storage system. So by using these, we have solar and PV and wind farms that are variable output and lag rotation inertia, and EV high charging demands and causes grid cognitions and voltage drops, and fast coming to energy storage, fast frequency regulations and crucial voltages. These are the overview of this uh, topic, and I hope you enjoyed this video. Thank you so much for watching. We'll see you next. Thank you.